Line up Venus, Earth, and Mars in your mind, and you're looking at three planets built from nearly the same blueprint, born beside the same star out of the same swirling cloud of rock and metal. One of them boiled its oceans into the sky and sealed itself inside a furnace of carbon dioxide thick enough to crush a submarine hull. One of them froze its rivers into dust and let its atmosphere leak away until the ground itself became the coldest thing for millions of kilometers. One of them kept every promise the other two broke. It held its water, kept its air breathable, and built an entire biosphere on top of the bargain. Distance from the sun doesn't explain that split because Venus, Earth, and Mars all sit inside the zone where liquid water can exist on the surface. Something else decided who lived and who died, and that something is a chain of planetary systems that has to keep firing correctly for billions of years in a row. Snap one link in that chain early enough, and a blue ocean world quietly turns into a desert, a snowball, a pressure cooker, or a bare rock with no story left to tell. Planets are cheap for the universe to make. Living, breathing landscapes are not, and the gap between those two numbers is the real subject of this video. Every rocky world starts life inside a spinning disk of gas and dust circling a newborn star, where grains of dust collide, stick, and slowly grow heavy enough to pull in more material through gravity. That construction site is a demolition derby. Infant planets smash into each other, get thrown into new orbits, have their surfaces melted twice over, strip each other's early atmospheres away, and get flung into the star or out into open space. The planets that come out the other side rarely look like Earth, because a small shift in the raw materials on hand turns one world into a scorched rock, another into a mini Neptune wrapped in gas, and a third into a giant with no solid ground at all. To even qualify as a candidate, a rocky planet needs enough mass to hold an atmosphere down against space, but not so much mass that it drags in a crushing envelope of hydrogen and helium while it's still forming. It also needs carbon, water, metals, and radioactive elements arriving in the right ratio, because those radioactive elements are what keep a planet's interior hot long after its birth. None of that material shows up pre-assembled into an ocean and a breathable sky. It starts out locked inside minerals, buried in ice, dissolved in molten rock, and trapped in gas waiting for a volcano to release it. Formation hands a planet its ingredients, full stop. Whether those ingredients ever reach the surface, stay there, or settle into a workable climate is a separate fight that gets decided afterward. By the time biology even becomes a possibility, a young planet has already survived a filter where the number of failure states outnumbers the number of ways to end up mild and stable. Astronomers start narrowing the search with the habitable zone, the ring of orbits around a star where a rocky planet receives enough sunlight to keep water liquid on its surface. That boundary is useful for a first pass, but it's really just a temperature guess built for a planet whose actual atmosphere hasn't been measured yet. The moon sits inside our sun's habitable zone and receives the exact same sunlight Earth does, yet its surface bakes past the boiling point of water by day and drops far below freezing by night. With essentially no atmosphere to speak of, there's nothing there to spread that heat around, hold pressure, carry moisture, or cushion the swing between day and night. Mars sits in that same broad zone too, out toward its cooler edge, but its air is so thin that the carbon dioxide it holds can't trap enough heat to keep rivers flowing across the surface today. Venus receives less than double the sunlight Earth gets, and yet its atmosphere traps that heat so efficiently that its ground temperature climbs high enough to melt lead into a puddle. The orbit only decides how much energy arrives. The atmosphere decides what happens to that energy once it lands, and that second decision matters more than the first. Nitrogen sitting in a planet's air builds pressure, but pressure alone doesn't trap heat. That job falls to water vapor and carbon dioxide, while any clouds floating above them handle a completely different task, bouncing a share of incoming sunlight back into space before it ever reaches the ground. Adjust that mixture, or change the pressure it sits under, and the exact same orbit ends up supporting a rolling blue ocean, a frozen glacier, or an oven that sterilizes everything underneath it. Liquid water forces a planet through its own narrow gate, because a world has to acquire that water without immediately losing it to space or burying it too deep for chemistry to reach. Too little water, and you're left with shallow pools that evaporate the moment the atmosphere thins out. Too much water, and you build one continuous global ocean so deep it seals ordinary rock away from seawater entirely. Push an ocean past a certain depth, and the pressure at the bottom crushes water into an exotic form of ice on the seafloor, which shuts down the exchange of minerals that long-term chemistry depends on. A properly balanced world looks completely different. Rain lands on exposed continents, rivers grind minerals down and haul them into the sea, and volcanoes dig buried compounds back up into the open air. Water isn't just a biological ingredient sitting in the background. It's the delivery system that physically connects the sky, the rock, the climate, and the chemistry running inside every living cell. Holding onto that water depends entirely on pressure, and holding onto pressure depends on a planet's gravity, its temperature, the radiation pouring off its star, and how geologically active its interior still is. Up in the highest layer of any atmosphere, gas molecules are constantly bouncing around at different speeds, and the fastest of them eventually pick up enough velocity to break free of the planet's gravity entirely. Small planets bleed gas fastest of all, especially once ultraviolet light starts cooking the upper atmosphere hot enough to rip water molecules apart into loose hydrogen and oxygen. Hydrogen is light enough to escape first, taking the signature of an entire vanished ocean with it into space, while the leftover oxygen either reacts with surface rock or finds its own way out through other escape routes. That slow leak turns a planet's entire history into a race. Gas rising up from volcanoes and geysers below against gas bleeding away into space above. Mars entered that race with a real head start. Rivers, standing lakes, a noticeably thicker atmosphere, and an interior hot enough to power a planet-wide magnetic field. As that smaller planet cooled down faster than Earth ever did, its global magnetic field faded out. Volcanic activity slowed to a crawl, and the raw solar wind started stripping charged particles straight out of its upper atmosphere. Once the pressure dropped low enough, surface water had nowhere good to go. It froze solid, boiled off into the thin air, escaped to space, or sank underground where sunlight can no longer reach it. Mars didn't die in one dramatic afternoon. It lost its magnetic field first, its thick air second, and its rivers last, and each collapse made the next one arrive faster. Venus took the opposite road and proved something uglier. A planet can hang on to a massive atmosphere forever and still lose absolutely everything that made that atmosphere worth having. Stronger sunlight drove more evaporation, and the water vapor rising into the sky acted as its own greenhouse gas, trapping extra heat that pulled even more water up off the surface in a feedback loop that kept feeding itself. Once that loop outran the planet's ability to radiate heat back into space, the oceans finished evaporating directly into the atmosphere, where sunlight tore their water molecules apart for good. The hydrogen escaped to space, the liquid water disappeared permanently, and the carbon dioxide left behind just kept piling up because the wet geological processes that would normally lock it back into rock had already shut down. What's left today is a planet nearly Earth's exact size, buried under crushing pressure, wrapped in clouds of sulfuric acid, with a surface locked permanently beneath heat that never lets up. Mars is the story of a planet losing its blanket. Venus is the story of that same blanket turning into the thing that kills you. Step outside our own solar system, and the most common stars in the galaxy. Hand every orbiting planet a brand new problem, because red dwarfs are smaller and dimmer than the sun, but violently active while they're young. Their habitable zones sit close in, tight against the star itself, which parks any orbiting planet directly underneath a fire hose of ultraviolet light, X-rays, flares, and streams of charged particles. A planet that close finishes an entire orbit in days, not months, and the star's gravity locks one hemisphere into permanent daylight while the other side sits frozen in permanent night. A thick enough atmosphere can carry heat from the scorched daylight side over to the frozen night side, stopping the air itself from freezing solid and softening the extremes on both faces of the planet. But that protection only lasts for as long as the atmosphere survives whatever violence the star throws at it early on. During a red dwarf's furious youth, an entire ocean evaporates straight up into the atmosphere, where radiation rips it apart and drags its hydrogen off into space piece by piece. By the time that same star finally calms down, the planet now sitting comfortably inside its habitable zone has already gone bone dry. The zone moved into exactly the right place at exactly the right distance, and the water was already gone by the time it got there. Timing decided the outcome as much as distance ever did. Bigger, calmer stars build wider habitable zones and give planets more breathing room. But even they brighten slowly as they age, and that slow brightening eventually forces every climate riding beneath them to adjust or break. No planet gets one permanent setting from its star. It spends its entire existence living underneath a lamp whose output, radiation, and total lifespan keep changing the whole time. Earth answered every one of the sun's changes with a thermostat built out of 5 ordinary ingredients: carbon dioxide, rain, exposed rock, Active volcanoes in the slow grinding motion of its own crust. Volcanoes pull carbon dioxide up from deep underground and dump it into the sky, adding extra greenhouse warming, while rainwater falling on exposed continents absorbs that same gas and reacts directly with the silicate rock underneath it. Rivers then carry the products of that reaction down into the ocean, where the carbon locks itself into layers of sediment on the seafloor and eventually gets dragged back down into the mantle by the motion of tectonic plates. Temperature sets the pace of the whole cycle. A warmer, wetter climate speeds up that rock weathering reaction and pulls carbon dioxide out of the sky faster, while a colder climate slows the reaction down and lets volcanic carbon pile back up in the atmosphere. This loop never locks Earth onto one fixed temperature. What it does instead is drag the climate back off the ledge every time it drifts too close to a permanent extreme. Every piece of that mechanism has to show up at the same time. Take away the exposed rock and rain has nothing to react with. Take away the volcanoes and the carbon dioxide never gets resupplied. Take away the internal heat and the whole system stops moving altogether. Bury the continents under one endless ocean, shut the volcanoes off, seal the crust into one solid shell, or boil away every drop of rain, and that thermostat immediately loses the parts it needs to function. Plate tectonics turns Earth into an unusually good recycling plant, constantly manufacturing fresh seafloor, dragging carbon-loaded crust back underground, pushing new continents up into the air, and exposing brand new rock for weathering to chew through. Moving plates aren't a default setting for rocky planets, though. The crust actually has to crack, sink under its own weight, and keep sliding instead of hardening into one single rigid shell that never moves again. Venus never got there. Its outer shell is one largely frozen, unbroken lid. Mars started with active plates, but lost most of that internal motion once its smaller body finished bleeding its own heat into space. A planet's entire surface climate turns out to be wired directly to events happening thousands of kilometers straight down, inside rock that no living organism will ever physically touch. Heat trapped deep inside a planet drives melting and volcanism up top, while a churning liquid metal core generates a magnetic field that deflects a large share of the charged particles streaming off its star. That field isn't some kind of unbreakable force field. Venus proves you can keep a dense atmosphere without one at all, but a magnetic field still changes how stellar particles interact with the gas sitting in the highest layers of the sky. Gravity leans on temperature. Temperature leans on atmospheric chemistry. Atmospheric chemistry leans on volcanic resupply, and magnetism quietly shapes all three from underneath, which is why no single feature on that list guarantees a planet's survival by itself. A planet's overall size ends up controlling most of those features simultaneously, which turns raw mass into a trade-off rather than a straightforward advantage. A small world cools down fast and can't hold on to gas for long, while an oversized rocky core drags in a thick primordial atmosphere during formation and buries its own surface under pressures nothing like Earth's. Somewhere between those two extremes sits a workable range where rock, air, and internal heat coexist, but landing in that range only solves one piece of a much bigger puzzle. The planet also has to avoid an orbit stretched into a long, lopsided ellipse, because that shape roasts the surface every time the planet swings in close to its star and then freezes it solid every time it swings back out. Rotation sets the length of a day, drives the circulation of the entire atmosphere, and shapes the weather patterns that decide where heat and moisture end up piling up. A violently tilted axis forces brutal, extreme seasons onto a planet, while a stable, gentle tilt spreads any long-term climate shifts out across timescales that entire ecosystems can survive and adapt to. Earth gets a meaningful dose of that stability from the Moon, which formed after a colossal impact and is heavy enough on its own to steady Earth's rotation and drive its tides. That same impact melted a huge fraction of Earth's surface at the time, which proves that even a collision violent enough to reshape an entire planet doesn't get the final say over what that planet eventually becomes. What actually decides the outcome is everything left standing afterward, whatever atmosphere survives, whatever water is still around, an orbit that still works, and enough quiet time afterward for chemistry to start over from scratch. Time turns out to be the resource hiding underneath every conversation about habitability, because a pleasant surface that lasts 10,000 years and one that lasts 4 billion years are, for all practical purposes, two completely different planets. Simple life just needs a single opening. Complex life needs that same opening held open through changing starlight, shifting continents, rising and falling oceans, transformed atmospheres, and the occasional asteroid slamming into the surface. Earth survived giant impacts. planet-wide ice ages, eruptions large enough to blacken the sky, oceans that rearranged themselves entirely, and mass extinctions that wiped out most of what was alive at the time, without ever crossing permanently into the kind of dead end Venus or Mars ended up in. Every one of those recoveries depended on systems that kept running quietly underneath the disaster, restoring the planet's chemical cycles and keeping small refuges alive where organisms hung on until conditions improved. Once life got established inside those systems, it stopped being a passenger and started becoming part of the machinery keeping the whole planet running. Early microbes rewired the atmosphere's chemistry from the inside out. Photosynthesis eventually filled the sky with oxygen, and biological activity took over the movement of carbon, nitrogen, and a dozen other elements across the entire planet. Forests then sped up that same rock-weathering reaction across every continent. Plankton grabbed the carbon those forests released and hauled it straight down into ocean sediment, and the living soil left behind kept rewiring how water and gas move between the air and the stone underneath it. A living planet isn't a dead planet with a few organisms sprinkled on top for decoration. Given enough time, the biosphere itself becomes one more working part of the machine that keeps the whole environment stable. That sets up a brutal requirement for any distant world hoping to follow the same path, because non-living processes have to keep conditions workable long enough, entirely on their own, before life ever shows up to help carry the load. A young planet that loses its ocean early never gets the chance to build that partnership at all, no matter how favorable its orbit looks a billion years later. Chemistry itself needs a constant supply of imbalance to work with, because life pulls its energy specifically out of the differences between light and dark, hot and cold, oxidized compounds, and reduced ones. A planet sitting in total chemical equilibrium is still full of matter, but it's offering almost no usable energy, the same way a battery goes dead the instant both of its terminals finally settle to the same charge. On Earth, sunlight lands unevenly across the surface. Hydrothermal vents shove heat and raw chemicals up from below, and weather drags all of it into constant motion, and that non-stop disruption is exactly what feeds metabolism from the surface down to the deepest ocean floor. Cut the circulation and useful compounds just sit there, locked apart from each other, doing nothing. Cut the renewal and every reaction eventually burns through its available fuel and stops. Real habitability, in the end, is active imbalance held together inside a stable frame. A planet churning hard enough to keep feeding life, but held steady enough that the churning never tears the whole system apart. That exact combination is rare, precisely because activity and stability actively work against each other. Aggressive geology keeps nutrients flowing, but also brings violent eruptions with it, while a quiet, sleepy interior keeps things calm, but eventually shuts circulation down completely. Even a perfectly engineered planet still has to answer to everything else moving around it, because neighboring worlds and leftover debris keep reshaping orbits and surfaces on timescales longer than any single human civilization. Giant planets constantly redirect comets and asteroids passing through a system, flinging some of them straight out into interstellar space while shoving others directly inward toward the inner planets, so their so-called protection cuts both ways depending on the day. Nearby planets trade small gravitational tugs back and forth across millions of years, and those tiny nudges eventually add up until an orbit drifts unstable or a climate cycle turns genuinely severe. Crowded systems built around red dwarfs pack several planets into a region smaller than Mercury's own orbit around the Sun, which ties every one of those planets' long-term histories together, whether they like it or not. A living world was never an isolated marble floating alone in space. It's one moving piece welded into a much larger machine built out of a star, its moons, its neighboring planets, drifting debris, and enormous stretches of time. When astronomers spot an Earth-sized planet sitting at the right distance from its star, all they've actually found is the outline of that machine, not the machine itself. The next step is figuring out whether that planet kept its atmosphere at all, and if it did, whether water ever reached the surface, carbon settled into a working cycle, and the star gave the whole process enough time to actually finish. Clouds can hide the ground completely, hazes can fake the chemical signals telescopes are looking for, and the razor-thin ring of atmosphere a telescope manages to catch only carries scraps of an entire planetary history, not the whole story. That's exactly why one promising dot of light in a telescope never becomes a confirmed second Earth after a single measurement, no matter how familiar its size and orbit look on paper. The search stays difficult for a very specific reason. Dead planets hold on to the exact same basic ingredients as living ones: Mars alone is still sitting on enough water ice to matter. Venus never actually lost its carbon or its atmosphere, it just lost the water. Out past Jupiter and Saturn, entire oceans hide under ice moons whose surfaces have never once seen sunlight. The raw ingredients turn out to be common everywhere you look. Keeping those ingredients organized into something durable is the genuinely rare part. Earth never locked in habitability once, back at the moment it formed, and then coasted on that win forever. It has been actively re-winning that fight over and over against atmospheric escape, climate feedback loops, giant impacts, and a sun that keeps getting brighter with age. Every river, every cloud, every volcano, every microbe, and every slowly moving tectonic plate is quietly doing its part in that ongoing defense, even though not one of them was ever designed with that job in mind. What looks from space like one calm, still blue sphere is actually a violently dynamic balancing act, held together by countless separate flows of energy and matter running at the same time. Most planets settle into far simpler, far duller states instead, permanently frozen, cooked into a runaway greenhouse, hiding their oceans deep underground, locked under one rigid crust, stripped bare of atmosphere, or buried under gas so deep there's no solid ground for life to even stand on. Those dead states stay dead precisely because once the water, the air, or the geological cycle vanishes, the exact processes needed to bring any of it back vanish right along with it. A planet has countless different ways to fall into permanent death. Long-term surface habitability is one narrow ridge running between all of them. None of that turns life into some kind of miracle dropped in from outside the laws of physics. It makes life the direct result of nature managing to hold an unusually long chain of connected conditions together without letting go. The more planets we discover out there, the sharper the line becomes between a world that briefly brushes up against habitability and one that actually holds on to it for good. Venus and Mars are sitting right next door to us as the two closest lessons available, and each one shows a completely different way that same chain can snap. Somewhere between Venus's furnace and Mars's desert, Earth is holding on to an outcome that distance from the sun never guaranteed, oceans sitting under a constantly changing sky, kept alive by a planet that's still burning hot on the inside. Somewhere else out there, another world has assembled that same kind of continuity out of completely different raw materials, a completely different star, and a history that looks nothing like ours. Finding that world takes more than just spotting water or clocking a temperature, because the actual signature of a living planet is an entire world working through time, not one lucky snapshot of it. Until that discovery happens, every silent, dead landscape we've already found is quietly explaining why dead worlds dominate this universe, without needing one single universal cause to blame. A planet is easy for the universe to build, and just as easy to break apart afterward. Staying alive against everything working to shut it down is the hardest trick any planet can pull off, and Earth is the proof still standing between two ruins.